Welcome to another installment of Mr. Strauss's Chemistry Corner. Today we pick up where we left off yesterday with the riveting story between particles and waves. Are these oh so different after all? So I hope you enjoy today's episode as much as I did. So the Heisenberg Uncertainty principle can also be stated as an equation. The equation is delta x times mass times delta v is greater than or equal to h over 4 pi. The delta x stands for the uncertainty in position. The m is your mass in kilograms. And delta v is your uncertainty in velocity. Now, momentum p is equal to your mass times your velocity. And since mass times delta v is present in this equation, we could also represent this equation as delta x times delta p is greater than or equal to h over 4 pi. So delta p is the uncertainty in momentum. So let's do an example problem here. Let's calculate the uncertainty position of a car moving at 3 miles per second with an uncertainty of 0.10 meters per second. So we've got a 1,000 kilogram car. It's moving at 3 meters per second, and it has an uncertainty of velocity of 0.10 meters per second. So my mass is 1,000 kilograms. My uncertainty in velocity is 0.10 meters per second. Do not confuse your velocity with your uncertainty in velocity. 3 meters per second is my velocity, but my uncertainty is 0.10. So we're going to find the uncertainty in position. So my equation is delta x mass delta v greater than or equal to h over 4 pi. Solve for delta x. Plug in my numbers. I'm dealing with a single car, so it's 6.626 times 10 to the negative 34th joules times seconds. Divide that by 4 pi times my mass, which is 1,000 kilograms, times my uncertainty in speed, which is 0.10 meters per second. Then I'll plug that into my calculator. And my equation will end up to be, my answer will end up to be Pretty darn small number. (5.3 times 10 to the negative 37 meters. That's my uncertainty in position. So we have a large car traveling at a slow speed. The uncertainty in position is very, 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 very small. So in other words, we're sure where a car is. For large objects moving at slow speeds, we know exactly where their positions are. But if it was a large uncertainty for, let's say, an electron, which has a small mass with a very fast speed, then the uncertainty would be high, the uncertainty in position. And so what ends up happening is your electron would appear as a blur. You would not be able to determine its location. So in summary, classical mechanics, the laws of Newton, work very good for large objects like planets. They work for objects moving with slow speeds, relatively slow. So things traveling 400 miles an hour is considered slow. And therefore, you will be able to come up with an exact answer. Or we would say, be determinate. Quantum mechanics, on the other hand, is for very small objects. And I'm talking smaller than an atom. At fast speeds, and then we will deal in terms of probability, not certainty. So for homework, I want you to do quantum worksheet number 2. In case you didn't get that, let me put that up there for a second. So once again, large objects, slow speeds, you get an exact answer, or quantum mechanics, small objects, fast speeds, and you deal in terms of probability.
Evening. It is now 4 p.m. Students, you need to be with a staff member or you need to be out of the building.
So,
Unsupervised students are at risk of getting a ticket. Good luck.
so for quantum worksheet number 2, well, first of all, I want you to do number 6 from quantum worksheet number 1. Okay, you now are able to do that. And then also for homework, I want you to do quantum worksheet number 2. Now for number 6 on quantum worksheet number 1, to find the uncertainty in your velocity, you have to take the change in velocity, which is the range. And the range of your velocity is 2.3 times 10 to the 8th meters per second, minusing 2.5 times 10 to the 8th meters per second. And so your change in velocity is 0.2 times 10 to the 8th meters per second. So that's where you get your delta V. Now where do you find your mass of your electron? that you go to Appendix I. Appendix I will give you the mass of neutrons, protons, and electrons. They are in grams. Your mass must be in kilograms, so make sure you can convert that. On number 5, on quantum worksheet number 2, the answer to number 6, sorry, on quantum worksheet number 1, the answer is 2.9 times 10 to the negative 12th meters. That's the answer. Number 5 on quantum worksheet number 2, as long as you are pretty close to the answers, you're okay. If you're really way off, then something else is weird. For number 6, nope. For number 7 on quantum worksheet number 2, the answer to number 7 is 1.6 times 10 to the negative 9 meters. But the rest of the worksheets are fine. So for homework, now you have all the equations and you have Appendix I to tell you the masses. Now it's up to you to figure out when to use the correct equation. And that homework, quantum worksheet number 2, is due on Monday. Okay, have a wonderful weekend. This is Mr. Strauss, signing out. Wow, what a riveting episode. I have to admit, I wasn't expecting that ending. So, I'd like to thank you all once again for tuning in to Mr. Strauss's Chemistry Corner. And hopefully we'll see you again next week, signing off with our traditional ending song. Skiddy-ma-rink-a-dink-a-dink, skiddy-ma-rink-a-doo, I love you. Skiddy-ma-rink-a-dink-a-dink, skiddy-ma-rink-a-doo, I love you. I love you in the morning and in the afternoon. I love you in the evening and underneath the moon. Oh, skiddy-ma-rink-a-dinky-dink, skiddy-ma-rink-a-doo, I love